Yeah, hello everyone here in the room and also to the audience online to the battery breakout session. My name is Roman Buchheit and I will guide you through this session the next 2 hours. And first of all, I want to start with the electrochemistry and the battery team at Math to Market. I thank my colleagues very much who helped to contribute to the content what I will show in the next half hour. In the electrochemistry team, there is Steffen also here in the room, and Ilona. She is in the hydrogen breakout session, so she cannot be here now. And then we have Janine, who is in the support team, so she is in the workstations. When you want to test GeoDict 2025, you can go to her. And we have our developers, Fabian, Sebastian, and Sven, and also the developers in ITWM who are doing the best solver. Falco is here in the back. And then also Jochen Zausch and Jan Lamme. Yeah, I want to show you very shortly the timeline for the breakout session. So after the welcome, there will be an introduction into the new possibilities of GeoDict 2025 and battery simulation. And after that, there will be a talk from my colleague Max, and he will present the development of a validated simulation model for all solid-state batteries. Then there will be a short break. And after the break, I'm very happy that we will have a talk from Robert Mücke from Forschungszentrum Jülich, also about solid-state batteries, but more focus on mechanical properties. And in the end, I want to end with a live demonstration, how you can set up a simulation with lithium concentration-dependent parameters with GeoDict 2025 and why this is important for some simulations. Okay, yeah, I want to start with just a general introduction. Why do we sit here? Why do we think about batteries? And this is just a market projection of the battery market until 2030. And batteries are very important for different applications. You have the consumer batteries in household devices, but then also other forms of batteries like these coin cells or the lead-acid batteries that are well known in cars. But then also, of course, lithium-ion batteries. That is maybe the most important battery technology nowadays because you get the highest energy density. And you see here that the market is expected to double until 2030. So there is a large potential here. And this market is booming. So I just looked up some headlines of the past month. And then you can see there is a lot of news going on. So the demand is growing, but also the materials used in the battery are sometimes critical. So you want to make good use of the raw materials inside of your battery. Then there is new technologies coming up, the sodium-ion battery, for example, but also silicon anodes. We have seen in the morning in the plenary talk from Professor Lee some work on silicon electrodes also. And of course, also solid-state batteries are under investigation. They have some advantages, but also challenges. And then to get more practicability, people also try to go into fast charging and also high voltage battery packs. And yeah, it's very booming, but as you can see, a lot of news and competition in the market. And some companies also say it's too risky. So that was an example from a company who said, yeah, they don't want to go that step to really get into the market. because if you want to catch up, you need to be really fast in the development, and the investment costs are also high. And we think here the digital material design can really be of help, because with digital material design, you get fast results, so you have a shorter time from research to the market, and you can test in digital experiments many different technologies. You can test many different parameters in the battery, like different chemistries, different particle sizes, different geometries of the electrode. And you can do a lot of this digitally and then focus your experimental approaches to the promising prototypes that you find in the simulations. So with digital material design, we believe that you can reduce the costs and also the risks in this battery design process. And this enables you then to adjust the battery to the application that you have. Like, for example, now for grid stabilization with a lot of renewable energies in the electricity system, you want very large batteries like a container from a ship. And this is for grid stabilization. So in the evening, for example, when no light is shining, the battery gets discharged and stabilizes the grid. And here you want high energy density and low cost with a high capacity. But also because it's a large battery, it should have, of course, high safety. For mobility applications like electrical cars, you have maybe another focus on high charging speed, because if you have a break, you don't want to wait too long until you can go on again. And the well-known batteries from consumer electronics, like here the laptop computer or also cell phone, there you maybe want to have first a high energy density because the device should be small, and still you want a good battery life, but also a good life cycle stability, because a phone, for example, is doing a full cycle every day, and you do many more cycles in 1 year than when you have an electrical car, because usually you don't discharge the complete battery of the car every day. And we have many companies already making use of digital material design with GeoDict. And yeah, there are just some of them are on this slide, but maybe I want to focus on this statistics I have seen. So that is the 7 biggest battery cell producers. And I'm very proud that 5 of them are also using GeoDict to improve their products. And yeah, I want to show you now what you can do with GeoDict and battery research and battery development. And I think you all know roughly how a battery works. And here you see a microstructure of a LFP cathode. And that is a FIP SEM 3D scan of the electrode. And when you segment the scan with GeoDict, you can distinguish all the different components. So you have the active material, you have the electrolyte phase, and you have a binder and carbon black network for mechanical stability, but also for the electron conduction network. And it's very similar like when you imagine a city with a complicated traffic. You have some spaces where pedestrians can walk. If you have a river, then there are big ships on the river. They are very slow, but they can transport a lot of material. And then you have cars in the driving way. And in order that the traffic works well, all the different parts need to be adjusted. So there must be enough space for all of the different components. And very similar it is with the battery. So the lithium ions need to be to move in the active material. There is diffusion in the particles. Then the ions are transported in the electrolyte phase from one to the other electrode. And the electrons must reach the active material from the current collectors via the CBD network. And that all this is really working well together, you need to improve the microstructure. And that is what you can do with digital material design. And the question is now, how do you start this? And I want quite shortly show you how you can digitize a scan. It was already mentioned this morning. So when you have a FIB-SEM scan, you have secondary electron image. You can do segmentation with AI tools, only using a single image stack. But here in this example, you see that there are still some errors in the segmentation. So here there is some active material segmented in the binder network. And what you can do, since the last GeoDict version, you can use two image stacks, so also the backscatter electrons. And by using the secondary and the backscatter electrons, the AI segmentation is combining both informations, and then the segmentation result is getting better. Then we are also working on the method to create a three-dimensional microstructure from a single 2D image. And for this, we have now 2D to 3D GeoApp and the new GeoDict 2025. What you can do here is you create only one single 2D cross-section image of your sample. That is much cheaper and easier to get than a complete 3D scan. And what the GeoApp is doing, it's analyzing the segmented 2D image, calculating the statistics from this 2D image, and then creating a three-dimensional digital twin. And then in the result, you get the difference in the two-dimensional statistics of the digital twin and of the original image. And then you see here that this matched quite well. So all the errors, pore size distribution, granulometry, and so on were 12% or less. And because we took this image from a complete 3D scan, we could also validate the digital twin in 3D against the scan in 3D. And by comparing the tortuosity in the electrolyte space, you see that also this tortuosity matched quite well. That was an example from a cathode electrode with NMC particles, but we did the same also with a graphite anode. So we have a single image from a graphite electrode, and then the GeoApp will create from this single 2D image a digital twin in 3D using the statistics from the 2D image. And also here the tortuosity between the digital twin in 3D and the complete scan in 3D matched quite well. So you can try this out now yourself in the new GeoDict version. Okay, but what can you do now if you have microstructure of the electrode inside of GeoDict? And just to show you the potential of the microstructure optimization with digital methods, I just want to stress out the question of binder content in a cathode, because here you have a classical problem in material science. When you increase the CBD phase, so more binder and carbon black in the sample, then the electrical conductivity of the electrode will go up. But at the same time, you have less pore space available and the ion transport will get reduced. So the ion diffusion inside the electrode goes down when you have more binder. And the question is now, how can you trade off between these two different properties of the electrode? Because you need both. You need good electron conduction and you need good ion diffusion. And what you can do with GeoDict, you can just check how is the capacity of this cathode structure with different binder content when you do a 2C charging until 4.2 volts. And if you do this with GeoDict, within 1 day, you get all the different data points here. And then you see here, the best result was at about 2.5% binder content for this example. And that was just in 1 day using simulations. And if you would do the same in a laboratory, then you would need several weeks to prepare all the different electrodes and then do the electrochemical experiments. So this can accelerate your development quite a lot. And in the end, you get 0.5% increase in the cell capacity compared to the initial value. And first you might think, okay, this is not so much. But if you think you have a large battery factory, for example, Tesla has the gigafactory close to Berlin, and there they produce 100,000 electrical vehicles a year, and they need about 100 million cells for all these electrical vehicles. And when a single cell has 0.5% more capacity because the microstructure is improved, then they can save around 450,000 cells a year, and this means you have almost 7 million less dollar you spend. So there's a big potential in this because the scale effect is quite large when you go to a production level. Yeah, how can you generate the different microstructures? And here I only want to shortly mention our structure generators in GeoDict. So we have granular structure generators and also GeoApps for this. There are GeoApps to create anode structures and also cathode structures. And with these GeoApps, you can just create with the mouse click microstructures here with different areal loading. So high area loading would be for higher energy density and lower area loading more for high power application. And yeah, it's very easy with these GeoApps to create the microstructures. Okay, so far I have talked a lot about how can I get the microstructure. You do the segmentation of a scan, you use the 2D to 3D GeoApp, or you create the microstructure with the structure generator. But what can you do then when you have the microstructure? And you can analyze different physical properties in order to improve the reliability and safety of the battery. For example, your customer asks for a certain lifetime of the battery, so you want to have control of the degradation mechanisms. Or you also want to have a safe product, so you don't want that there is any issue with the battery during operation and that it catches fire or something. And for this, once again, the microstructure is a key, because if you know what is really going on the microstructure level, you can also evaluate what are the risks for degradation mechanisms or possible security issues. And yeah, I will just show you some of the new things that we introduced into the new GeoDict 2025. One of them is the heat production inside of the battery. So here you see a graphite NMC battery, and it is charged at 1C charging rate from 3.5 volts until 4.1 volts. Yeah, during this charging, of course, a lot of energy will go inside of the battery. But part of the energy that you put into the system will be dissipated into heat. And the question is, where does this heat come from? How much heat is produced? And here we have now a new feature. You can see now the produced heat inside of the battery. And you can see the heat power over time in the different components of the battery. So how much heat is produced in the cathode, how much in the anode, and how much in the electrolyte phase. And you do not only get this plot over time, but you can also get the 3D information. There you can look on the details and not only have a look on the average heat produced. For example, if you look on the electrolyte heat, then you see here that there is one hotspot here close to the separator where you have some bottlenecks, so all the ions need to go through this small section. And here you have quite a lot heat produced. The anode active material, graphite, has most of the heat on the surface of the graphite particles towards the electrolyte, because here the ion exchange is taking place. But most of the heat is produced in the NMC particles, because here you get the concentration gradient and then the diffusion of the ions. So this allows you to learn much more details, and also you could, for example, try to improve the microstructure that the total produced heat is less. Another degradation mechanism is the mechanical degradation. And how can you imagine this? So if you have a car and you go with your car into a car park, and you do this many times, like you go to work every day, then at some point you might hit a wall and then you have a small scratch on your car. And when you are in a hurry and you do the parking not carefully, but you go very fast in the car park, then you have a higher risk that you have such a damage of the car. And very similar it is also for the battery, because with every charging and discharging, you introduce lithium ions into the active material and you release it again. And all this insertion of lithium ions will lead to an expansion of the volume and to a shrinkage. And if you do fast charging, then even this mechanical stress is larger on the active material. And with the battery degradation module, you can visualize the mechanical stress and strain due to intercalation of lithium. So first you do electrochemical measurement, you know where is lithium ion concentration change, and then you do the mechanical simulation, and then you know, okay, I get this stress and strain inside of my structure. And one important feature that we were asked in the past were the boundary conditions for this module, because so far it was not possible that you have a certain defined external stress or strain on the volume domain that you simulate. But for example, the all-solid-state batteries, they are always operated at a certain external pressure. And now in GeoDict 2025, we have a new boundary condition for the battery degradation, that you can put an external stress or external strain on your structure while you are doing this battery degradation simulation. Next, I want to show the degradation mechanism lithium plating. So what is lithium plating? This occurs especially when you have fast charging. Then it might be that locally you don't insert the lithium ions into the anode material, but you plate metallic lithium on the surface of the anode material. And in the worst case, you will get lithium dendrite growth and maybe even penetration of the separator, and then you have a short circuit, and it could be that the battery is on fire, and this you don't want. So it's good for you if you know, can I estimate the risk of the lithium plating at certain conditions? And here you see very fast charging simulation. So it was 3C charging rate. This means in only 20 minutes you fill the complete battery from empty to full. And you can visualize the plating potential on the surface of the anode active material. This is the local potential between the electrolyte and the active material. And if this potential is below 0, then you know you have the thermodynamic requirement fulfilled for lithium plating. And as lower this value is, as higher the risk of the lithium plating is. And here you see that the highest risk of lithium plating was close to the separator. So this helps you to to estimate this risk and also maybe improve the microstructure to reduce the plating potential. Okay, so I showed you different possibilities to look on the details of the three-dimensional simulations of the batteries. And the question is now, okay, how can you perform the electrochemical simulation with GeoDict? And we have, in general, two different models implemented inside of GeoDict. So what I was talking about so far was the fully resolved model. So you do the simulation on the three-dimensional microstructure. We have two different solvers there, the LIR solver and the best micro solver. And you get all the details on the three-dimensional structure. But the problem is that this is quite high computation effort. So, for example, when you look on this example structure and you do the charging from 3.5 volt until 4.1 volt, this took around 9 hours with the best micro solver and needed about 65 gigabyte of memory. And the classical model often used in battery development is a homogenized model. That is a Newman model. And you simplify the simulation to a one-dimensional problem because basically the ion transport is going in this direction. And the good point of this method is that you get results very fast. So with the homogenized model, the calculation time was only 20 minutes. And also the memory was much less, so only 2.3 gigabytes. And the charging curve of both different models is quite similar. But the important thing to use the homogenized model are the effective parameters. So you need information because all these electrodes are homogenized. You need information. How's the effective electron conduction in the electrode? How's the effective ion conduction and so on? And the question is, where can you get these parameters from? And here also GeoDict can help you because you have the fully resolved three-dimensional structure inside of GeoDict. And if you do a homogenized charging simulation, then GeoDict will calculate all the different effective parameters for the anode and also for the cathode. And it will also report all the calculated parameters in the result report. And these parameters are then used in the best meso solver for the charging curve. But of course, you could also take the effective parameters that are calculated. And if you have your own in-house Newman model with some adjustments, then you can also use these parameters calculated from BatteryDict. And this is a good way if you want to test many different microstructures, then you can do parameter studies. You get very fast the charging curves. And if you have one microstructure that looks very interesting in the homogenized model and you want to know more about it, then you can do a fully resolved simulation on that microstructure. Then we have some new features in the electrochemical simulation. And one of them is that you can now use up to 4 different materials for carbon binder network or also for conductive additives in a single electrode. So far, it was only possible to use one material for the CBD phase, for example. And what can you do now with the new possibility? So it's known from the literature that the conductivity in the CBD phase is not the same all over the battery electrode, but due to the fabrication process, you have a gradient in the electronic conductivity. And you can now use 4 different material IDs to represent the areas with higher conduction and lower electron conduction in the CPD phase, and then perform electrochemical simulation. Or you could say, I have core shell particles, like particles with coating, for example, ion conductor or so. And that would be this yellow, the yellow coating on the gray active material particles. And then you have still the CPD phase as the red material ID. And yeah, you would then use both in the electrochemical simulation. Or you can say, I want to use active material. I have my CPD phase, that's the red part, and I have conductive additives, for example, vapor-grown carbon fibers. And you can simulate such a structure now because you can use up to 4 different additives in the charging simulation. Then we have some smaller adjustments. With the new GeoDict 2025, you get the full control what volume fields are written into your result. So you can select here in the output tab the different physical properties, and then you can save hard disk space because you only save what you really need. And we improved the output. So if you enter all the mass densities of your materials, then you can get the cell potential curve also as a function of the mass cell capacity, which is useful if you want to compare it with experimental data. And with this, I want to end my talk with a short outlook, what we plan to do next. So there are many different things we are working on. I maybe only focus on some of them now. Together with our partners from ITWM, we are working to also bring electron chemical impedance spectroscopy into GeoDict. First, it will be an expert setting, but later we also want to have it in the GUI. Then we also work on the electrolyte saturation. So when you fill the electrolyte into the microstructure, that you get a time dependent saturation. And we are working on all solid state batteries. That will be the talk from Max, who comes next. And in the end of this session, I will show you concentration dependent parameters. At the moment, you need an expert setting for this, but in the future, we want to make it more easy that you can use it from the GUI. And with this, I want to end this first talk. Thank you very much for the attention. You can always ask me if you have questions about this, or book a meeting with me. And yeah, if there are any questions now, you can ask, and thank you.